Hello, welcome to our report on Rust. My name is Nicholas here,
And I'm Nicholas Gilliran.
and we have some interesting things to speak to you today regarding the Rust language. It is a different feel than most other languages that you might know. If this is your first introduction to Rust, it will all feel very natural. But again, if you're coming from a C++ world, some of the concepts covered in Rust can feel different to you while you're learning it, but we assure you they're for the benefit of the language itself.
Yeah, so we're going to start with just a little bit of background to get you prefaced for Rust, why you would use Rust, what are the purposes of Rust, what makes it even a language worth choosing. So one of the main priorities of Rust is its safety. So it prioritizes memory safety and concurrency safety. So it makes sure that when you're doing concurrent programming, there's no data races. It uses a borrow checker to ensure that. Yeah, so Rust is going to be great for developers that really want speed because it gives developers control over all the low-level processes on the computer while still maintaining a lot of features that make high-level programming languages easy to use. So Rust kind of hits the best of both worlds while giving developers full control over what they want their program to do, so that when they hit compile, it'll do exactly what they expect.
So, a little bit of history about the Rust programming language itself. It was created by Graydon Hoare, and um, the desire was actually born out of an elevator incident that this person had. They lived many, many flights of stairs up into their apartment building, and they got there after work one day and not expecting to have to climb that many stairs just to get home. This person uh, really had an epiphany about how unreliable or how cumbersome some C programs have become with embedded electronics, and therefore decided to make their own programming language out of this unfortunate incident for them. And then they were employed at Mozilla during the development of this, and Mozilla supported the developer throughout this entire process and really threw its weight of its large company behind them, and has developed into the program that it is today.
Yeah, so now we'll be looking at a lot of the basic features in Rust to kind of explain just all the parts of it.
All right, so through the Rust documentation, to their own admission, as we can read this quote here, we won't debate the issue of what functional programming is or isn't, but we'll instead discuss some of the features of Rust that are similar to features in many languages often referred to as functional. And so that key takeaway is that Rust is multi-paradigm and doesn't initially trying to fit into any box that other languages have been developed from the start. There are the language itself harkens to object-oriented programming in some instances and functional programming in others, and trait-based, and you get this third kind of mix of multi-paradigms that we see with Rust. It does seem that can get overbearing, and it can be at times, but again, Rust's key design feature is that it's fast and reliable, and taking the best of all of those worlds for its use case really allows Rust to be efficient and effective.
So next we'll look at data types. The data types in Rust are pretty standard. They're pretty much what you expect from any modern language. Its primitives are split into two types, scalar and compound. Scalar being single um, value data types. So something that holds a single value like an integer, which is a number without decimal, floating point, number with decimal, Boolean, true or false, or a character, which is which Rust uses the Unicode representation of. Rust also has compound primitive types, both tuples and arrays. Tuples being lists of data that doesn't necessarily have to be of the same type, while arrays, of course, do have to be of the same type. Rust is a statically typed language, so these data types do need to appear and be recognized at compile time, but the compiler is rather smart and can infer a lot of that. we'll look at the integer data types in Rust because there are 12 of them, which is a lot, but each of them being signed and unsigned take up a different amount of space. So it gives the programmer a lot of availability to exactly decide how much memory each variable needs to take up to give them that control over their processes.
So control flow, as you might expect in other languages, we do have loops, and more loops in order to exact control over the processes in a continuous runtime environment. Again, that's one of the founding reasons for Rust is to have long-term reliable programs in order to limit the number of downtime or to limit the amount of downtime that you might experience in that use case. The traditional control structures are available to the developer, examples being if then statements, if condition, then follow this code block. We also have for loops and while loops, so that way you can set your conditions based on the types of data that you're working with in order to elicit the expected response. And it also allows you to pick that particular portion of Rust up as a developer easier since it is so characteristically like other ones.
So next we'll look at expressions. Rust is an expression-based language. It very clearly delineates between expressions and statements. Statements being instructions that perform an action but return a value, and expressions always evaluate to a resultant value and can thus return that. So as we see in this code that is on screen right now, a let or a declaration of a variable doesn't return anything, so you cannot set a value equal to a let statement. So expressions can be literals, functions, or of course mathematical expressions, which is what we would expect from a lot of other languages. The order of operations in Rust, so the precedence levels of what things in an expression get evaluated first is very similar to that of C++, with function calls being done before a lot of the multiplication, which is done before addition and so forth. And it is context dependent because of that. So it gives developers the ability to create these complex expressions while still knowing that it will do exactly what they want it to do.
Okay, so the subprograms, like my colleague was saying, those functions and expressions, Rust does allow for a single point of entry and multiple return points. In those subprograms, especially the ones in the structures, again, structures resemble an object in other languages, and so those methods in and of themselves can be abstracted away. Most notably with those, the inserted argument into that method is at self and ensures that that subprogram is run on the instance or the portion of memory that that instance of a structure is taking up to ensure proper binding of that particular method. And the use of that is encouraged when you're working with those class or the structure private methods.
So now we'll look at the object orientation of Rust. So as we mentioned earlier, it has some aspects of object orientation and some aspects of functional programming. So we're going to look at a few of the most major concepts that are included in object-oriented languages and see how Rust implements them or if they do it all. So the object stand-ins for Rust are going to be structs and enums. Which allow you to store both data and behavior, which is that key concept of objects in object-oriented programming. One major difference that this has between other object-oriented languages is that the data and behavior are separated. You must declare the structure first and then implement them later in the code after declaring the structure. Encapsulation is the next thing we'll look at, which is basically the idea that you can privatize certain methods or variables is basically using the private or public modifier. And Rust does allow for that. By default, everything is private, but you can use the pub keyword to make your methods public. and allow others to use them. Inheritance is where Rust starts to deviate from object orientation because it does not have direct inheritance as you'd expect from an object-oriented language like Java. It does not allow you to create a structure or what would be an object in our case and have another structure inherit all of its methods and fields. So there is no direct inheritance in Rust. So that key component is missing, but it does solve this issue through, or all of the issues related to inheritance through traits, which are basically interfaces. So to look at an example of how you'd create object-oriented code in Rust, here's a struct declaration on the left, which has the fields, and then the implementation block on the right, which implements the methods. You can see they are separate. They're not encapsulated in one class file, as you'd expect from a lot of other languages. And here is an example of traits, which is the thing that allows Rust to have polymorphism. You can create traits and have structures implement those traits, which can still give Rust the ability to do polymorphism in its code without taking on all of the problems of direct inheritance that they considered when they created the language.
As with most code, when we write, we are going to, by way of operators using our code or programs, or just by ourselves writing the program to be deficient in the first place, we are going to have exceptions. And Rust handles exceptions in two ways, or thinks about them in two ways: recoverable, which obviously gives the developer a chance to make a decision on continued code execution, and also something that is very useful in Rust to deal with, or to have an option of recovering your code, is the result type, which will actually inform your decisions on how to handle that exception and continue on with your code. And then there's non-recoverable. This can either be induced by Rust at runtime, or it can be chosen by the developer. If you can no longer recover your code based on certain parameters that you set for yourself, you can call the panic macro, and it will terminate runtime.
So next, we'll start evaluating the language, see how it stacks up to other languages, its simplicity, how easy it is to use, as well as how powerful it can be.
Okay. Simplicity, or closely tied to orthogonality, as you can read there in our quote, basically a relatively small set of primitive constructs combined in a relatively small number of ways. Rust exemplifies its orthogonality through the relatively small aspect of this definition given to us from the book. It may seem like a lot to have multiple portions of integers in the primitive types, and it may seem like there are a lot more primitives than there are in other languages. However, this is to the benefit of Rust, and it is still a relatively small number of primitives. And the book further mentions that orthogonality is closely related to simplicity, and Rust simplicity is on display with the revision count, more specifically the lack of a 2 or a major breaking change at the leading edge of the revision count. So that way everything is backwards compatible, and something that you wrote in Rust maybe a year ago, let's say you're trying to get back into the language, will still compile, and you can take advantage of all the optimization that they've developed since then, and your code will still run. So it makes it more simple for a developer in the long run with Rust, because your projects are not going to start failing due to software revisions from Rust themselves. With the, again, like we said, with the backwards compatibility, and that in and of itself increasing simplicity, and might not seem orthogonal, and it does have a oddly weird revision number. They're all always leading with that 1 again, but there will never be a Rust version 2.0, and that is how Rust increases its simplicity.
When looking at the control structures in Rust, they're very, very standard. there's not a whole lot to look at comparing them to other languages because of, how very similar they are to basically any programmer. So any programmer that knows any other language is going to understand how to use the if statements, the while loops, the for loops. I think the one, maybe different thing that Rust has than some languages, it's the infinite loop, just with a loop keyword. But, very simple control structures, very effective. Not much to say about that.
Okay, so an evaluation of data types, like we said earlier, the 12 different integer types that we have here, again, look like a lot, but in terms of readability and writability, there is that slight increase. But when we go to evaluate the language itself, it is much more memory efficient in this manner by not requiring 128 bits to keep every potential type of int that you could have there. This speaks highly to the increase in reliability, as we don't run out of memory, or we're not handling memory efficiently and causing our programs to run ad nauseum on a group of data sets that may take 5 or 10 times longer, just based on the data size that is used. So the data types, while getting that minus for readability and writability, has a very large plus when it comes to reliability.
So the syntax design in Rust can be somewhat complicated due to it being a statically typed functional language. You have to be explicit with a lot of your declarations, which, when comparing it to something like Python, which implicitly does a whole lot for you, Rust can be a lot more difficult to pick up because of that. But despite all of these more things that you have to explicitly declare, it is able to make it simpler to write and read using abbreviations. Like when you're declaring a function, it uses fn. When you're implementing blocks, impl, and the data types that we were just looking at being simply the I and then the number of the size needed for the variable itself. So because of this, it's still very simple to read if you know what you're looking at. It is the syntax of Rust allows you to look at other Rust code and know exactly what the programmer intended, because you'll be able to see the data types that are supposed to be returning. You're able to see exactly the errors that things are returning. It's very clear in its syntax, but that does make it somewhat difficult to pick up because of how much you have to explicitly state.
Abstraction in Rust, again, the more abstract we can get and the more human readable, human writable we can get in a language, the higher we consider it on the chain of languages. Rust does have traditional abstraction through structures and enums to hide away modules functionality and to make things private. Again, taking away the need for the developer to understand every single function or overwhelm them if they're just using a certain type of functionality from your program. Rust does have that support for abstraction. And we also have abstraction, or the overbearingness of the type definitions or the type declarations with the new type pattern. So that way, instead of the long form verbose typing of a type throughout the entirety of your code, you could actually just use the type aliasing, and that's just for a name. It's not truly pointing to the same location of memory. It's just a type name aliasing to help you read and write in a more human oriented way. So it supports the abstraction of the complexity of a computer in that way. And then and again, those certain types of abstraction, along with others that Rust provides, help to increase the feel of a high-level language to the developer.
So expressivity is the next thing we'll look at, which measures basically how it enables the programmer to do complex tasks simply. The more convenient options increase the expressivity of a language. And there are a few ways that Rust does this. A couple very clear ways that we can look at are loops and slices, which allow you to create these structures very simply using something that is easy to think about and visualize and just simply put it into the code. So for example, when we look at this for loop, we see for number in 1 to 4. We can very clearly see the range that it wants instead of having the C++ version of a for loop where we have to declare the iterable variable and then tell it when to stop and how to iterate. It's still all there and it's still very present, but it's a lot easier for us to read and easier to type without all the extra semicolons and parentheses. And slices are a very similar thing. It allows you to get copies of other arrays or other structures without having to do that manually. The slices allow you to simply grab certain sections of code or certain sections of your data and manipulate them either affecting the original or not. And as you can see, it's just as simple as creating a new variable and taking the section of a previously declared variable, and it'll create a copy for you. And it's all very simple. It gives the developer a lot of power with very little overhead.
As far as type checking in Rust, Rust is statically typed. Again, all of those types need to be known at compile time. But like we talked about earlier, there is good support for abstraction to remove the overbearingness of traditional statically typed languages for the developer. It makes the developer have the ability to have their coding environment be more user-friendly specifically to themselves while enforcing the good characteristics of a strongly statically typed language. And then again, this results in far fewer runtime errors, resulting in reduced maintenance costs for deployed applications. Again, going back to that initial use case, which is embedded software and having the ability for that software to run for a long time without a problem.
So when looking at the exception handling in Rust, I think it's very simple the way it expresses it, having that panic, which is very clearly something that can will terminate your code, versus the result, which can encapsulate all other types of errors. The exception handling in Rust is very interesting because it doesn't interrupt the flow of code like other languages using try catch blocks. It still uses them very simply. Things that can return errors will return an error, and then you simply use a match statement to check that. It makes it very clear when something will return error and what you do if it's actually bad versus if it's okay. So it's effective, very effective at handling these errors, propagating them up, as well as just treating them like you would other values by just assigning them to variables and being able to match them to other error types and all the such. And all of it is built into Rust. You don't have to bring anything else in, which is very good for its simplicity and writability for developers.
Restricted aliasing. Rust does not set boundaries at compile time for aliasing. This is done to increase optimization of memory, and there are provisions to use the unsafe keyword in order to circumvent or utilize unchecked outside code. One of the reasons why Rust needs you to use the unsafe keyword is because of the considerations made when developing Rust in order to optimize the use of memory. In other words, other languages may allow you or permit you to have two pointers accessing the same piece of memory, and then you would only find that you had an issue with that chunk of memory later on during runtime. And Rust's assumptions is that we don't want that to happen, and therefore those assumptions going into the compiler's functionality enforces a very strict utilization of memory aliasing.
That's a lot of the information you'll need about Rust. So to simply reflect on it and talk about what we like about it, what we don't like about it, one thing that we looked at while we were creating our code and studying the language was the compiler. The compiler is very, very useful at locating your errors, explaining them to you cleanly, and then also giving you suggestions on exactly how to fix them. So in this above code, here's an incorrectly defined function, and it very clearly states where the error is, what the problem is, as well as giving you a few, like a list of a few potential fixes, explaining when you would use each type of fix. Also, each time it gives you one of these, it gives you a code that you can put in to find exactly more documentation on all of the errors that you're receiving, and just get more in detail. So the compiler basically can teach you the language just as you're creating it. So if you're coming from another language, you can type code how you would expect it to run, and the Rust compiler can basically teach you as you go. Our final kind of thoughts and summary of Rust is that it is kind of difficult to pick up because of how safety forward it is. It wants its memory to be safe. It wants all of the types to stay static. It is very much in favor of making sure everything is exactly how you want it to be, and that nothing unexpected happens. But this does kind of make it, yeah, this makes it difficult. This reliability and safety, it works in favor of the language because that's what its purpose is to be an incredibly safe language. But this adds a level of complexity that a lot of languages don't have.
An analogy that I like to think about is that it's guardrails during a round of bowling. And this, when you're learning to bowl, potentially you may hit the guardrails, but eventually you wouldn't need them, or rather need them less. And to that end, you would need the guardrails less, but you also wouldn't admonish their existence because they taught you how not to rely on them. And Rust does the same thing. It teaches you and helps enforce the rules of not going into the gutter, not having runtime issues. But as you progress in the medium and long term with Rust, you do appreciate those things being in place, not really relying on them in order to ensure safe memory, but appreciating that they're there and knowing that you're getting one of the fastest high-level programming languages available to developers today.
So now we're going to look at a little bit of Rust code to see, how it works, see it in practice. So we've implemented a merge sort algorithm. Here we can see, here's a function declaration. Here we have all of the input types, everything you're inputting into the function, but no return type. Return types are denoted by an arrow, but we can see that a lot of these variables here, they're all let variables. We don't explicitly describe what they are, and then the compiler recognizes the value that we're trying to assign to them, as well as all the variables that we will assign to them later. So it looks at not only the declaration itself, but every time we use them, it checks what could it potentially be, and based on what is seen, it categorizes this as a U size. So Rust code in that way takes the simplicity very, very well. Of course, you have to declare everything as mutable because Rust emphasizes safety. Anytime you declare a variable, it doesn't want you to change it unless you explicitly tell it to. So here, if we can move down to main, we have a string of numbers. We can print those numbers using a print line macro, and then we can run the merge sort on it. And we pass in a mutable address of the numbers, allowing us to actually change the array of numbers instead of returning a new one that we'd have to reassign. So this merge sort code will recursively call itself, so that way it can split up the array into smaller and smaller chunks, and it does this by getting slices. So this kind of x0 ... m will give us a slice from the 0 element to the m element, and then that will get passed into this merge function, and then use that slice of the array that we were looking at, edit it, do what it needs to do with it, and then return it back. And in our case, change it because we are letting it be mutable. So if we can simply run the code, we can see the before and after. Of course, the merge sort did complete. It was correct, and it was the sort itself was very fast as we would expect it to be. Um, Not sure if you noticed, it did take a second to compile the very first time because of um, how much Rust has to do at runtime, asserting all of those variables and making sure everything is memory safe. But once you run it, it is blazingly fast, as they say, and allows you to do exactly what you want to do. So this is kind of just a simple example of an application of Rust code.